Okay, so we can start also today. It's really a pleasure to have here today Roberto Benzi, who is a professor at Tor Vergata and who gave many key contributions in statistical physics, among which the most relevant are perhaps stochastic resonance, turbulence, and the application of the lattice-Boltzmann equation. And in particular, he will talk about noise and something related to the stochastic resonance, a phenomenon, a discovery, which he witnessed together with Giorgio, Angelo Vulpiani, and Alfonso Sutera. So please, Roberto.
Okay, thank you, Giacomo, and good evening to everybody. Most of my slides are in Italian, but I will speak in English. And it will be very easy to follow for those who are not Italian speaking the discussion. So usually when I speak about stochastic resonance, I start to make a story on how it was discovered and which were the fundamental steps and so on. Today, I will try to introduce the argument in a completely different way. I want to discuss first of all, what in physics we consider the noise, and how we can use the noise in some cases, and eventually how it was introduced for the problem of climate and for the phenomenon of stochastic resonance. Now, the very first thing I want to point out is the work by Einstein, where for the first time the idea of noise was viewed from a different point of view with respect to previous works. Now, we know in physics, noise is something that we want to avoid. Now we do experiments, we do simulations, we do many things where there are anyway some perturbation, and we want to clean up this perturbation by averaging and by doing other things. This is not the case when you look at the Brownian motion. The Brownian motion is a particle that is moving endless in a system like this, and the problem was to understand how it was possible for this particle to have an endless motion in a liquid. And that was a problem on the table for many years, and Einstein put forward what you know very well, the idea of the solution that comes from the intuition that atoms are real stuff and not just a theoretical point, theoretical things. Now, this idea of Einstein was the starting work of Perrin, that in about 2 or 3 years, if I remember correctly, was able to show that, in fact, the Einstein prediction was correct. And for the very first time, it was discovered that the assumptions that atoms are real are, in fact, true. And that is the first time that the noise, comes into physics to explain something that was not clear. Now, today, we have a possible definition of noise that is very qualitative, looks like the following. Everything that is small and is a small perturbation to our system can be considered a noise. The point is to have a small effect in a very short time. This is what we generically think about noise. Today, we are able to do with the thermodynamical noise, the one that Einstein was working on, a very sophisticated thing. For instance, this is an optical trap, an experimental system, where you can put the particle on a kind of harmonic potential here inside the trap, and you can look at the behavior of the particle, of course, a Brownian particle, inside the system. You can build up things like this, and you see that this is a very sophisticated shape of a trap, 2 traps together, which allows you for the particle to go from one side to the other. And in fact, if you look at the signal, you see something like that. The particle is here, then it jumps there, and it goes from the other side. And the jumping between one side to the other, due to the thermodynamic noise, is random. I mean, it's well defined, but random in time. Now, this is an important point, which comes into the play when you want to understand the stochastic resonance. Suppose that you have this particle inside the double well, as we have seen before. Then, for the particle to go to the other side, you must have a rare event, something where the particle is due to the noise, is moving on the right for n consecutive steps. Roughly speaking, I mean, if you say that P is the probability to go from here to there, then the probability to reach the top of this double well potential and eventually to go on the other side goes like P to the n, where n is the number of steps that you need to do. And in fact, the correct statement is that if you know this potential well, delta V, and you know the variance of the noise, the characteristic average time to go from the one side to the other is an exponential value of the steps. That is the potential variation, the potential difference divided by the noise value. So this is something that you can check directly experimentally, and you can develop a very well-defined theory for that, where you can compute both the statistical properties and the average properties of the switching time between one well to the other, and close, if you wish, some of the effect of thermodynamic noise on a single particle in a potential well. Now, the situation can be, however, more complicated. And this is already a big step. Suppose that you take a fluid like this. And suppose that, as has been done experimentally, you take a very thin layer of fluid and you put some energy in this point here, red, and you can measurements here in this on this line or the other line as well. So this has been done in 86 by Sommeria to study what happened in turbulence on a two-dimensional plate. Now, there is a long story about two-dimensional turbulence, but to make the story short, what happened is that essentially energy pile-ups to the very large scale, and then you can have two kinds of circulation, one which is counterclockwise and the other one which is clockwise. Now, suppose that you put yourself here, the green point, and you look at the current that you can measure. Then what you observe is something like that. You see, from the point of view of the circulation, the average circulation, what happens is that essentially turbulence is acting as a kind of noise, and this noise, I mean, the variance is due to turbulence, and of course, cannot be tuned so easily, but this noise is able to make a transition from one possible state to the other, okay? Now, if you don't believe to this possible explanation, what happens is you can make a comparison, okay, between a direct numerical simulation of the Navier-Stokes equation for the system that we were looking before, which is on the right, and a numerical simulation of a double well with the noise. This is a comparison between the two cases. This is a very abstract system. This is the case of circulation, and you see that there are jumps, okay, at random times, which are introduced by the effects of small-scale turbulence. Now, this is a crucial point because it implies that from the point of view of the circulation, what you call deterministic behavior, which is small-scale turbulence, can be considered as noise. And most of the time, if you look at the power spectrum of the time of any quantity, like the velocity or other quantity, you don't see a spectral gap, something which is on the large scale and something which is on the small scale. there is a continuous kind of gap, and this is a little bit confusing. But in fact, it is I mean, it's a prejudice to have a spectral gap in order to speak of noise. Now, something similar is supposed to occur in many other cases in physics, and not only in physics, but also in astrophysics and in solar physics. For instance, we know that the system like Earth has a magnetic field, and in fact, the magnetic field show reversal on the average, every 250,000 years, okay? And we know that there are reversal, and for a very long time, there was a problem to understand why there is the formation of the magnetic field, which is called a dynamo, and why there are reversal. More recently, okay, in a series of papers done by Stefan Fove and other people, the effect of dynamo was in fact explained experimentally and numerically. And once again, okay, this is the experimental situation. And once again, you observe this transition from one state to the other, which has randomly in time. Now, the situation is still the same as the very simple case of the double well. Now, of course, you are not able to make an explicit computation of the average transition time, but once again, you can do a numerical simulation where you can compare, okay, the double well potential behavior with the nonlinear turbulent situation for the case of the experiments, and they look very similar. So the real point of this discussion is not that you make transition from state to the other, is that there is a kind of general definition of the noise and of rare events induced by the noise, which are similar to the one that you consider when you speak of noise in terms of thermodynamic behavior. Now, we can make another step, which is absolutely different. Instead of looking at physical system, we look at something which has to do with turbulence in terms of the original word, the meaning of the word. Now, turbulence comes from Latin and means disorder or confusion and a lot of. So turbulence means a lot of confusion. And we use this meaning of the word still now. I mean, you say the child is turbulent. The crowd is turbulent. So because of that, with a group of friends in Eindhoven and somewhere else, we decided to study more carefully the behavior of the original word of the system turbulence, which is crowd, and see whether or not the effect of noise can play any role. Now, these are the bunch of people, including myself, that participate to the work. And for this work, we got even a recognition, but it was a lot of amusing. I mean, it was really something that was extremely amusing, okay? So now let me switch a little bit to show what was the problem. Okay. Okay. Let's see whether I can start the movie. Okay, what is the point? The point that we assume people are walking in a place. Okay, for instance, take a railway station as we did in Eindhoven. Let me say that it's easy to do it in Eindhoven because privacy problem there is a little bit less constraining than here. Okay, but we took this camera, and the camera were taking the track of individual paths. And this is what happens. You see that there are the people that are moving, and you see the track. All the people are connected with the line. Okay. Now you have 2 years of people going out inside the railway station with the tracks. And then you can study how what is the dynamics of this system. Let me see if I can. Oops. Doesn't work. It doesn't work any longer. I want to go back to this presentation. Okay. Okay. So these are the track. And so we decided to study all this track in order to have a clear understanding of the possible parameterization, if you wish, mathematical formulation of the track of these individuals. Then we started to study one of the simplest possible problems, which is the following. You take a corridor. Here is the corridor, okay? The corridor is going from the entrance of the university to the cantina. The corridor has no window, no side, nothing. No. And so the people, what people does is usually to enter the corridor to go out here or the other way around, okay? And you see that while there is an average path inside the corridor, there are all the people that you are inside. I mean, we take the case of one people each time. So we neglect the case of 2 people, 3 people, and so on. If you consider only 1 people and you look at the trajectory, you see that the trajectory, individual trajectory is not, of course, a straight line, not even close to the average, but is making some oscillations around the average, okay? And then we decided to look at these oscillations here as a kind of noise. I mean, we do not work on a straight line. When we work, we move around. So the basic idea was saying, okay, let's consider that the people moves in this direction, okay? And then eventually make some oscillation because it doesn't move straight. And this kind of oscillation we consider as a possible noise. I mean, this is outside the physiology of the system. We are not moving with the noise, but I mean, from the point of view of the path, is can be considered as a kind of noise. Now, we can compute the variance of the noise, and we know by definition that the people can go in one direction or in the other. And so we can compute the probability for one people to stop inside the path and to go back. And then if you compute this probability, which the only fitting parameter is the variance of the noise, you see that this is the darker sign is given by this parameter, by the fitting of this parameter, assuming that you have a double well potential, and the red line is what you observe experimentally. So in other words, everything goes essentially as in double well case, okay? Even if in this case, the noise does not really exist. It's just the way you are walking around. You can think why you can make such a prediction by looking people walking and trying to guess or to make the estimate of the probability to go in the other side. The point is the following: when people move in one direction, of course, there are a lot, they can think a lot of things. For instance, they can think that they forgot the phone. They can think that they have to make shake hands with the friends and so on. So they can slow down and they can eventually move on the other side. Okay? And now we come to the real point of this talk, which is the case of the stochastic resonance. The only thing that we understand from my previous discussion is that, in fact, the noise can give you a mechanism, quite generic mechanism, which introduces a large deviation in your system. Large deviation means that you have the finite probability to observe a very rare event. In the beginning of the 80s, we were discussing with Angelo, Alfonso Sutera, and Giorgio, the problem of glaciation and climatic change. Now, the point is very simple. If you take, according to our friends, specialists in climatology, especially in the ice core, if you take the ice core and you can reconstruct the variation of temperature on the Earth over the last few millions years, and in particular, the accuracy becomes quite good over the last 1 million years. And what you observe is a periodic variation between a glacial and interglacial period. Everybody knows that the climate of Earth is experiencing glacial interglacial period. Now we are living in an interglacial period, and it's supposed that in 32,000 years, more or less, we should enter into a glacial area, if we can, okay? And the question is how it's possible to explain this behavior. Now, at the time, one of the suggestions, in particular due to Imbri, was to consider this effect as due to the change in the Earth eccentricity, which is in fact has a period of 100,000 year cycle. So this change in the Earth on the Earth eccentricity was discovered many years ago by Milankovitch, and you can also compute how much such a change in the orbital parameter introduce, how much change in the solar radiation is induced by the change of the orbital parameter. And if you do this computation, it turns out that you have 0.25 watt per meter square, okay? So we know such a period, and we know this effect. And then you can compute how much change in the temperature of the Earth is due, can be explained by this small change of energy from the sun. And you get 0.2 degrees. This is what you obtain. Now, 0.2 degree is much smaller than the 10 degree that we do observe induced between glacial and interglacial period. So it is clear that we have a problem. We have a problem because we cannot explain the factor, the difference between 0.2 and 10 degrees by using the brute force approach of change in the orbital variation. Okay. Now, consider the simplest possible climate model. You have ice, you have land or sea, you have clouds, and then there is an incoming solar radiation. I mean, essentially, the climate is working in a very simple way. You have a balance of energy on the Earth's surface. The balance of energy, of course, is not uniform over the Earth. You have the polar, which is colder than the equator. You have different heat flux between each different surfaces, and then there is a motion to trying to equilibrate this such a difference. But the very basic mechanism is the balance on the Earth's surface. So it is necessary. The first thing one has to do is necessary to look at the surface temperature or the surface temperature between the incoming and the oncoming radiation due to the sun and to the Earth. Now, there is an incoming radiation. This incoming radiation is order 400 watt per meter square. Then some of this radiation is reflected back by the ice and by the clouds. And roughly speaking, there is a reflection which is about 30%. Then, of course, there is the surface of the Earth, which is becoming relatively hot because of this incoming radiation, which goes back and it produces an infrared emission, okay? So the overall balance is the following. You have the incoming radiation, 1 minus the reflection, the albedo, and then you have the infrared emission, okay? And the albedo, of course, it's this ratio, and this is the infrared emission. The basic idea to use this balance and the noise together came to us from a paper by Klaus Hasselmann that, in fact, got the Nobel Prize together with Giorgio Parisi and Manabe in 2021. Now, the idea of Hasselmann was exactly the same idea that I was trying to discuss before when speaking about turbulence, no? Turbulence as noise. Now, Hasselmann made the observation that if you want to understand the sea surface anomaly, variation temperature, on climate scales, you should take into account the variability of Earth atmospheric wind over the Earth. And such a variability was discussed by Hasselmann as a random noise. So he introduced the idea that there is a climate noise that can be taken into account to study some variation over a few years. Now, we took advantage of this idea, and when we introduced the noise in this model. So we take this model and say, okay, there is a day-by-day variability induced by the weather. We know, roughly speaking, what is the fluctuation of the temperature induced by this variability. We know what is the average relaxation time. So we can compute most of the parameters of this model, okay, from observation. And so we can take this information of using the noise, weather noise, on the climate balance model, and we obtain, okay, as a matter of fact, that if there is two states in the system, as the observation suggests, the glacial interglacial period, then because of the observed climate fluctuations and dynamic response in terms of relaxation, what we can predict that there should be transition over 50,000 years as indicated on average, okay? But unfortunately, this is a good step, but unfortunately, such transition, according to what I told you before, are random. They occur on random time, okay? They are not periodic. So these three guys with me, I mean, Giorgio Parisi, Alfonso, that unfortunately is no longer with us, and Angelo, okay? During a very, Giorgio usually is telling you that we discuss. Now, when Giorgio is saying we discuss, it means that there was a mess, going there or somewhere else place, and then we will discuss on the street, on the bus, or whatever. But essentially, we discuss, okay? Not in a room, but we discuss. And then we decided to make a step, quantitative step, with the original idea by Giorgio saying that, okay, on average, you have 50,000 years, but you didn't take into account the effect of eccentricity. If the effect of eccentricity is small, it can be small on the single well, but will be enough to make a jump almost periodically. Okay, so the basic idea of Giorgio was the following. At this point, we had a problem, and this is an historical remark, that while there is a theory of stochastic differential equation that can be used to predict what is the average transition time from one state to the other, okay, the case with an external forcing depending of time cannot be solved exactly. And the only way to understand what was going on was by using numerical simulation. And that is one of the things that we did, and the result is more or less here shown. This is the case without noise. This is the model that climate model, okay? And 1 minus 1 means 1 the interglacial and minus 1 is glacial. So this is the effect of the external force due to Milankovitch in the interglacial period. And you see that is almost irrelevant, okay? This is the effect of the noise as discussed by Hasselmann and revised by using the balance model by us. And you see that there are transitions, but they are random. And this is the result when you put the things together. Okay, so this is why how we introduce the model. Okay. Now the reason why it works is very clear. It was clear at that time, and it's very clear. Remember that from going from one well to another, you have this famous P over N term, which means that you must have a rare event to reach the top. Now, if the potential, however, is changing in time in this way, you see that from going from here to there, it's much more easier than the other way around, to go from here to there. And this means that you may almost surely jump when you are in this position or in this position and randomly in this position. So this was in the nutshell, the basic idea. And it works. It works very well. It works very well numerically, okay? And I'll tell you that there were a huge amount of criticism. I mean, huge in the sense that there were some mathematicians say this is wrong, okay? And we say, okay, this is wrong. Then they cannot prove that it's wrong, but they can feel that it's wrong. There were some experimentalists that were not believing, not to speak about the climatologists. And then in 1983, Stefan Fauve and others make an experiment where they will show that, in fact, our mechanism was correct. And inside the climatological community, there was the question that we were, you see, if you go back to this figure, you see that there is a sharp transition from one state to the other. And so the climatologists say, well, I mean, this is not true because we don't observe the sharp transition. We do observe something that is continuously changing in time. I remember a huge discussion in '83 at the Varenna Summer School on this point. At any rate, a few years later, I think it was the beginning of the 90s, it was shown from more accurate ice records that, in fact, the climate Earth experienced very sharp transition, okay? There are cases where on a period of about 50 years, the temperature was changing by 5 degrees. So it's a huge change. So there are sharp transitions. It was observed on Greenland and in other cases. And that was one major point that was in favor of this approach of stochastic resonance in the climate change. Now, this is another evidence of the same problem. It is clear that if the potential is going up and down, you can jump when it's up. But if you do not jump when it's up, you have to wait an entire cycle. So your jumping time can be every 1 period or 2 or 3. It's quantized. So if you look now at the record, you can see whether such quantization is observed in the climate record. And in fact, it is observed, okay? So something similar is in fact observed in climate change over the very long time scale. It is not obvious if we are now able to reproduce using the present state of general circulation model this behavior, but it's quite clear that most of the criticism that was put forward in the very early stage of our theory are now over, in the sense that we are able to convince people that this mechanism is a realistic mechanism. Now, that's the word why it is called stochastic resonance. I mean, we did together with Angelo the numerical simulation in the February 1980, and then just a few days after, I went to a meeting in Erich where we were discussing climate change, and actually Klaus Asselmann was there, and the big boss of climate theory, which was John Imbri, was there as well. So John asked me about the mechanism, what kind of mechanism we were looking, and he was thinking of a resonance, because this was his idea. So in order to convince him that this mechanism has nothing to do with resonance, I call it stochastic resonance. That is the reason why, okay? Maybe it's not the correct word, but I mean, it works. Now, just a final remark before I stop this short review. I mean, if you look at the climate over the last 64 million years, I mean, this is what you observe in terms of temperature. These are the cycle of 100-year cycle that we speak about. This is the last period. Look at this scale is in the logarithmic of time. Okay, there are jump, and you see that there are a lot of. If you go back, very back in the past, the temperature was much higher than today. So there is a. If you take this picture and you discuss the effect of fluctuation that we do observe over the last 200 years, which are here, then most of the people will tell you that probably there is no evidence of any climate change on the Earth. And this is the basic, very basic rule that people use when you want to deny what we do observe. But this is wrong. This is wrong because, I mean, it's true that we do observe this effect, but it's not the temperature what we have to look at. I mean, the correct way to look at the climate change is the following. Here in blue is the Milankovitch forcing. So in blue, there is the forcing that is induced by the change of eccentricity on the Earth, 0.25 watt per meter square, okay? So this is what is due to the sun, and this is what we discuss with the stochastic resonance. And this is what we believe can be the cause of glacial interglacial variation. This is our energy pumping in the atmosphere in terms of watt per meter square, okay, over the last 50, 60 years. Now, if you extrapolate such a number in terms of the energy balance, as we did for the Milankovitch forcing, what you get is about 2 degrees. So in 2011, this 1 watt, 2 watt per meter square, roughly speaking, correspond to 2 degrees increment of the temperature. So the way we have to look at the climate change is the difference between what is due to the natural variation of the sun and what is due to the anthropogenic effect. So it's not the temperature, the correct record, but it's the energy pumping in the atmosphere. I mean, this is a completely different point. And I think that the stochastic resonance was able, in some sense, to clearly point out that is not the effect of on the temperature that we have to look. Temperature is a proxy, but the real point was the balance in terms of climate theory. Now, stochastic resonance is a more general concept. After we did the work on climate change, we generalize it in the case of the deterministic system. So in fact, the effect of noise is marginal. But again, you can always think of noise in the sense of turbulence that we spoke before for the climate change. So you see, this is the one of things which come out from this comparison between what is the climate change induced by Milankovitch effect and amplified by the noise, and what we are doing now to the climate. Okay, with this observation, I think that we can stop and eventually answer a few questions if you have any. Thank you.
So thank you very much, Roberto, for the very clear and interesting seminar. I would leave room to questions and comments.
Yes, I have a question. And in your scheme, apparently the sun radiation is a constant of time. It's just the orbit, the distance is changing. But you have also cycles of the energy output from the sun.
Sorry?
What is, I mean, you have also cycles in time of the energy output of the sun, or is it almost constant? The quantity of energy that the sun is pumping into the atmosphere?
We have, but it's more the noise to sine ratio. It's very small, very large. Sorry, so we cannot be precise.
So this factor is not relevant. Okay, thank you.
No, io volevo ringraziare Roberto per questa bellissima presentazione e congratularmi di nuovo per il bellissimo lavoro con i pedoni. Spero che non avete dovuto avere 5 milioni e mezzo di consensi informati, sì, perché quello sarebbe stato pericoloso. No, la domanda che volevo fare è, ma uno si concentra sugli ultimi 800.000 anni, per buone ragioni, perché ci sono i dati molto precisi, ma ci sono delle evidenze di glaciazione più vecchie di 800.000 anni, cioè di oscillazione sui 100.000?
Allora, la risposta è più tecnica, è ma. Nel senso che è chiaro che 64 milioni di anni fa vi è stato un evento dirompente dal punto di vista climatologico. Se è vero, se è arrivato questo meteorite sulla Terra, e quello ha perturbato in maniera devastante tutto il ciclo energetico. Quindi è complicatissimo capire se, diciamo, su tempi scala di qualche milione di anni ci sia o meno una evidenza di glaciazione. Tieni presente che le informazioni che abbiamo sono dalla Groenlandia e qualcosina dall'Antartide. Tutto il resto non c'è. Quindi qualcosa riusciamo a dire, ma non credo che ci sia qualcuno che possa oggettivamente dare una risposta sensata a questa domanda. No, la cosa che si può aggiungere è che noi non abbiamo una definizione di stato del clima, questo è il punto. Quindi noi non sappiamo se ce ne sono due, come si osserva lungo il periodo degli ultimi milioni di anni, o più di due. Non abbiamo neanche idea se un eventuale spostamento del bilancio del clima possa produrre un nuovo stato, oltre che una forzatura. Okay? Da cui poi sia quasi impossibile tornare indietro. Quindi onestamente queste informazioni non sono a disposizione, anche perché non abbiamo ancora gli strumenti per farlo. Prego.
Come si misura la temperatura di milioni di anni fa?
Con l'isotopo dell'ossigeno 18. Da là si risale alla quantità di ghiaccio presente e si fa una stima per estrapolazione.
So I switch to English. So connected to the question of Federico. Connected to the question of Federico, you've shown in one of the graphs where with the historic from the ice. Also the dust.
You mean this one?
No, the previous one before you started with the stochastic resonance. Yes, this one. The red curve is the dust.
Yeah.
So this is estimated
No,
how and
the red is CO2 and the
it's not
sorry,
the
red is dust and the
red
green
dust.
is CO2.
Okay, this is also extracted from the ice, or how
Yeah,
you
from the
you,
sediment.
you see the percentage of
Yeah.
dust. Okay,
Of course, there are a lot of error parts.
of course, of course.
You have to take it back.
It is understood that the role played by dust. It is understood that the role played by dust on the climate.
Of course, the dust will introduce a decrease in the energy balance in the sense of temperature. I mean, it is quite clear that increasing the dust will reduce the temperature.
Yeah,
Okay?
but I mean, what produced the dust? I mean, at that time there were no industries.
This is
So
another story, because if you increase the temperature, of course, you may also have more dust in the.
okay.
Okay. You also see something else that is very asymmetric. Huh? This is due to the fact that probably what happened is that when you enter interglacial period, the number of clouds that are present is more. So this is the effect of the new state, the interglacial state. But then eventually this effect will disappear. There are theory for that. And then what happens is you jump on the other side and then you stay for a while the state disappears and you go back. And this gives you an asymmetry. Okay.
So one transition
You-
is sharp and the other one so one transition is sharp and the other one is much
The
slower.
other one is lower. Yes.
So it's more asymmetric, the potential,
Yeah.
than what
Of course, you can do the model for that, but it's not relevant. I mean, it doesn't introduce new physical effect. C'era Enzo? No, c'era Massimo.
Thanks, Roberto. This is I think, a nice situation, because there was a bright idea and you initially proved that was good by using numerical simulation. Then you had a number of, say, experimental proof. But what about, let me say, the theory, the mathematical basis? There's been any further study? Maybe Professor Gallavotti could give some hint about, because this is nice because you can apply to a very interesting problem, but maybe this idea could be applied to other fields if we have a better understanding of the mathematical basis. From this viewpoint, what is the status?
Because it depends whether or not you thinking of the stochastic differential equation in the mathematical sense, or a deterministic problem. Okay, if you think of a stochastic differential equation, you can play some game. Okay, you can do, okay, this is small, this is large, you can make perturbation, and then eventually you are able to provide reasonable approximation. Okay, which is more or less the hand waving argument that I was doing. If it's deterministic, then it's a different story, because there are cases where the fluctuations are themselves responsible to build up the state. If you switch, kill the fluctuation, the state no longer exists. And then the situation may be much more complicated. And there are different class of problems where people are looking at, but there is no general theoretical framework for that.
Yeah, I have a question about this periodic modulation you have on top. Is the phase the right one? I mean, I guess is the phase of this periodic motion. I mean, you showed that there are times in which is more favorable to jump and times in which is less favorable to this is okay with experiment.
Yeah,
I mean, this of course is something I guess people. So somehow, I mean, a negationist could say that when the last plot you show in which there is this input of energy from humanity, a negationist could say, well, look, we had all the time the risk to fall down in a glacial state, and humanity is saving us from the risk to fall down.
Yeah, that is correct, but you have to take into account the time scale. This is 0.25 watt per meter square for 50,000 years. Now we have 1 watt-meter square for 50 years. Okay, so you must take into account that the effect is different because the system takes a lot of time. I mean, it is true. The relaxation time of atmospheric fluctuation in first approximation order 10 years, 7 years, whatever. Okay, but you should remember that the time scale of the circulation in the ocean is 10,000 years. I mean, if you go to the bottom of the ocean, you see a temperature of 4 degrees, which cannot be explained otherwise unless you do not have a circulation. And such a circulation is over 10,000 years. So the time scale is different. So what is possible is that if you increase too much the forcing, you may build up a new state. For instance, some people believe that because of this effect, you may suddenly change and go to a glaciation instead of this can be done. I mean, there are theory for that. Okay. Fortunately, we hope not to make an experiment on this.
So other questions, remarks? George.
I would like also to make another comment. Can you show the slides on the large scale and temperature?
10 million.
Yes, the millions.
One.
Okay. Now you have, I think that you have, you see, you have marked the 1 point at, I think at, no, you are not marked. There is some change at 3 million here from.
This is 60 million.
Okay, no. This is 60. If we look at 3 millions, there is some decrease in temperature.
Yeah, because of the.
No, 3 million, not that.
I see. It's 50.
No, not that one. I say at 3
There's
million.
one.
Yeah, no more.
This one.
Not very.
This one.
No, here.
Okay, 3 million. No, this is
The region there is, I was speaking with someone that was studying the sedimentation on the sea.
Yeah.
And he says that there's a complete change of the sediments that are deposited on the sea in a period of 100 years, which means a very fast change.
Very, extremely fast.
3,100,000.
No, this is extremely fast, 100 years.
Well, I'm not at him, but he's a very famous, it was his PhD thesis, and now he's president of the Leopoldina Academy, so it should be.
Was a very good thesis.
So it should be.
Was a very good thesis. Okay, thanks.
So let's then thank again Roberto.
Wow.
Waiting for everyone.
Thank you. Va bene.